So I forgot to tell you in that last video, my recommendation on your blue paper when you write in the first part of the fundamental theorem of calculus is to write it like this. The derivative with respect to x of the integral from a to x of f of t dt equals f of x. And you'll have to specify that a is any constant. That's how it would look on your blue paper. All right, so some examples using the fundamental theorem of calculus. Here, the derivative with respect to x of the integral from 0 to x of 1 over 1 plus t squared dt. It meets the three criteria. I'm taking the derivative of an integral. The variable of differentiation happens to match the upper limit. This x, that is, matches this x, this is the top limit. And the lower limit of integration is a constant. All three are true. All I have to do is take that integrand, change all the t's to x's, and I get my answer 1 over 1 plus x squared. All right, so it turns out that two of those rules we can actually get around a little bit if they don't get met perfectly. So here's another example. It's on your paper. If I want to take the derivative with respect to x of the integral from 0 to x squared of cosine t dt, see, here's my problem. I needed this upper limit to match the x, and it's not a perfect match. But that upper limit is a function of x. We can finish this problem using the first fundamental theorem, the fundamental theorem of calculus, that first part, and then using the chain rule. So it's going to be, take that integrand, replace all the t's with whatever the upper limit is. So cosine t becomes cosine of x squared, and multiply by the derivative of x squared, which we know is 2x. There's your final answer. Okay, what if somebody makes the upper limit the constant and the lower limit the x? We can use that rule we know from properties of definite integrals to switch the limits of integration. So here the derivative with respect to x of the integral from x to 5 of some function. We really want that to be from 5 to x. We want the constant as the lower limit and the x as the upper limit. So switch the limits and bring a negative out to the front. Now I'm going to take the opposite of the derivative of the integral from 5 to x, and now it works. I'm just going to take that 3t sine t, change all the t's to x's, and then I have the negative from the front. All right, here's one more sort of variation, the way we can get around those rules. If I want to take the derivative of an integral, but neither the upper limit nor the lower limit is a constant, they both happen to be functions of this variable that I'm differentiating with respect to, I can use one of those other definite integral properties to get around this. So I can split up this integral. Instead of integrating from 2x to x squared, I can pick any number. It doesn't even have to be something I think is between 2x and x squared. Pick any number. 0 is obviously the easiest one to use. I'm going to change this to the integral from 2x to 0 plus the integral from 0 to x squared. So taking that area under and picking just some number to split it up into two sections. So here in this slide, they actually wrote those in the opposite order, but you can see that it doesn't matter. Now I'm going to take the derivative of the integral from 0 to x squared of this integrand. Here I have the integral from 2x to 0. Has the limits in the wrong spot. So I need the constant as the lower limit and the function of x as the upper limit. So I'm going to change this to subtraction and switch those limits. And now, for this first part, I'm going to use the chain rule. I'm taking the derivative with respect to x. The lower limit is a constant, the upper limit is a function of x. So I'm going to take that integrand, change all the t's to x squareds, and then use the chain rule, so multiply by the derivative of that upper limit. And then I have the subtraction sign I had here. I'm going to take this 1 over 2 plus e to the t, change all the t's to 2x, and then use the chain rule, so multiply by 2 at the end. So there's your last example.